Okay, so welcome to the live session for week 9 for the course Introduction to Semiconductor Devices, which is taught by Professor Naresh Kumar Imani from IIT Hyderabad. And I am Anant Singhal, a PhD student from IIT Jodhpur, and I'll be assisting you in solving similar assignment problems that are given to you in the week 9 assignment. So we'll be doing some of the concept, we'll be going through by clearing the some of the concepts first regarding the MOSFET, and then we'll be doing some of the numerical and conceptual problems as given in the assignment. So as we have already covered the content till week 8, so we have almost covered the basic physics or the base of the course. If we are able to understand the content till week 8, then there is no problem in understanding the content further, because what we have is we have already we now already know how to make a band diagram for any device, which we I guess did in around week 3 and week 4 lectures. Then we started our first device in which we made the junction with two different types of doping, such as PN junction, electrostatic, etc. And then we had some application of bias voltage, as we did for the applied bias and the spatial variation in the depletion region. And after that, we did the ideal MOS capacitor. We did the ideal MOS capacitor, in which we did the profiles of electric field and potential diagram, etc., such as accumulation inversion regions. We have already covered this part. And in the last lecture, we covered the threshold voltage of the MOS device, in which we read about some of the low frequency and high frequency CV measurements. How we do that? We apply a small signal pulse of AC over a superimpose over a DC, and then we saw some of the non-idealities that involve work function, etc. And at the last, we had a topic of high gate dielectric, in which we need to like understand the concept of effective oxide thickness, which was not discussed in the last lecture. So I'll be taking a very short topic of high gate dielectrics, like the concept of EOT basically. Why do we require high gate dielectrics, and what is this effective oxide thickness that we require? And in this lecture, majorly we'll be covering the content of the long channel MOSFETs, energy band diagram of the MOSFET. So since we already know the energy band diagram of a MOS cap, it is nothing but similar to that of a MOS cap only. And then we'll be seeing what is this VD, VG, that is a gate. We already know about G, but we don't know about the drain right now. So we will have certain more terminals in the MOS cap device that we are naming as MOSFET. Then we'll be seeing what is this of threshold slope, and some of the performance metrics that we do need for a MOSFET. So let's start. As you guys remember, in the last lecture, we have already covered the MOS cap with its CV measurements. And then I have done the CV measurements part, and I guess the calculation of threshold voltage was a major topic in the last lecture. We went from increasing the gate bias from negative to a certain positive voltage till we reach this particular threshold voltage. And if you remember, the threshold voltage that we got was nothing but the flat band voltage, which is due to the flat band. Then we apply some of the, then we deplete the carriers that will give rise to this Q depletion by Cox, this particular voltage, and at last we have 2 pi f for inversion. So this comes due to the inversion, this comes due to the depletion, and this is even before accumulation. So this we already discussed in the last lecture, but and this Q depletion also we discussed as a function of the doping, etc., and it came out to be under root I guess 4q Na epsilon s phi f, and where this psi s is taken as 2 phi f because of the depletion criteria. And what we left was we did not calculate the inversion charge. So let me quickly go through this inversion charge. So we have this MOSFET in which we had this oxide, we had this metal layer, that is the gate, in which we apply a certain VG voltage. This we already know now. And in the inversion layer, what we have the accumulation of minority carriers, that are the electrons near the semiconductor oxide surface. So this is what we already know, that we have this oxide So the total gate voltage, if I say the total gate voltage will be nothing but the flat band voltage plus the oxide drop, and at large what we have is a surface potential. So this is nothing but Tox. This drop is nothing but accumulated by the surface potential. So what I can write is the difference between the VG and the flat band voltage is nothing but oxide plus the surface potential. And what we know that we have charges should be equal, so Cox multiplied by Vox, that is the charges around the oxide should be equal to the depletion charge plus the inversion charge. So if we have this, so what I can write, Vox I can write as Q depletion over Cox plus Q inversion over Cox. So basically if we have this Vox, so let's say I'm naming this equation as 1, I'm renaming this equation as 2, and I'm putting 2 in 1. So once I have this 2 in 1, what I can write is Vg minus Vfb is Q depletion over Cox plus Q inversion over Cox, and plus what we have is plus phi s, which is the surface potential. And what we are interested in, we are interested in calculating this inversion charge, which will be Q inversion over Cox, which I can write as Vg minus Vfb and minus this Q depletion over Cox and minus phi s. So if we have this, so I can easily write Q inversion is nothing but, okay, I can still write Cox, so I can write Vg minus this, I can write as VFB plus Q depletion over Cox plus phi s. And if you remember the first line I wrote in the starting of lecture, that we came to know that the threshold voltage is nothing but the flat band voltage, the sum of flat band voltage, which is this term, the Q depletion over Cox due to the depletion when we deplete the carriers, and at last to make the inversion, the addition of this surface potential, which is 2 phi f, which is this particular term, which is nothing but Vt. So what we can write it as, Q inversion can be written as, okay, let's still write Cox here, Vg minus Vt. So Q inversion is nothing but Cox Vg minus Vt. So basically it is a linear function of the gate voltage, the inversion charge. So this is a very important relation in context to the derivation of the MOSFET that we'll be doing. So this is the inversion charge density basically, and this is per unit area. What I can write as NQ, which is nothing but Cox Vg minus Vt. So I can write this Q inversion as NQ, where this N will be number of electrons per unit area. Yeah, so this will be the basic motivation of going towards the MOSFET. So let's start. So I hope you will keep in mind this particular relation, which is the inversion charge. It is nothing but Cox times Vg minus Vt, which is per unit area. And let's now talk about the MOSFET. What is a MOSFET? So we have already studied this. This, let's say, is the oxide. This is gate Vg I'm writing, and this is always grounded. So what we have is metal oxide semiconductor, let's say P type substrate for now. So it is nothing but a MOS cap, which is nothing but a two terminal structure. So for MOSFET, what do we have? We have the same MOS cap, which is the heart of a MOSFET. So we have still this oxide, we have the metal, we have this Vg, we have the same substrate, and we have the same ground, the body. What we additionally have is around these or below the oxide layer, what we have is we have two additional implants, or by diffusion, what we have an additional source and we have a drain. So what can I say? If I have a MOS cap, as we studied in the previous lecture, which is a two-terminal device in which we had only VG, which is a two-terminal device. And if I just place two more implants, that is by either by diffusion or something, which are highly n doped, let's say n plus n plus, this is nothing but a MOSFET, which is a four-terminal structure. So since you joined late, I'll quickly go through what I have done till now. So in the last lecture, we have covered that the threshold voltage is nothing but the sum of the flat band voltage, the voltage drop due to the depletion charge, and the final one is the inversion charge. So if we have this threshold voltage, so we calculated the inversion charge particularly till now in this lecture, which is this. So the total gate applied voltage is a sum of the VFB. Give me a moment, just a moment. Yeah, so yeah, I hope I'm audible now. So the total gate voltage will be nothing but the sum of flat band, the oxide voltage drop, and the surface potential that we require to get the inversion. So this is what I have done. So we know that the total charge should be constant on either side. So this is the total oxide charge should be equals to nothing but the depletion charge. That is the depleted carrier. Let's say I make some depleted carriers. So this is the total negative charge and this is the charge over the oxide. So Vox times Cox should be equals to, sorry, the depletion charge and the total inversion charge. So total negative charge is basically equals to the total charge that we have on the oxide layer. From this, I wrote the Vx very simply as just dividing Cox on both the sides. I get the depletion plus the inversion by Cox. And I use this Vox particularly in this equation. And once I did it, I got this particular relation in which I was more interested in calculating the inversion charge, which will come out to be something like this. And once I take this minus sum as common, so I got to know that this is nothing but the flat band plus the depletion over Cox plus Is, which is nothing but the threshold voltage. So Q inversion by Cox is nothing but Vg minus the threshold voltage. And the inversion charge will is coming out to be Cox times Vg minus Vt, which is per unit area. So this is what I have done till now, the derivation of inversion charge. And now I was coming to MOSFET. What is the basic difference between a MOSCAP and a MOSFET? So we have already studied everything for MOSCAP and we saw that for a CV we have different curves for, let's say, a low frequency and high frequency because the electrons cannot respond to make the inversion layer for very high frequency. But MOSCAP in MOSFET it will not happen because we have ample amount of electrons that are present between source and drain. So we will always have a plot CV like this for a MOSFET as compared to let's say a a MOSCAP, in which for the very high frequency we were not going back again to Cox and it was something like this for high frequency if you remember, and this is for low frequency. So we'll always be having this. So now yeah, MOSFET is a four terminal structure in which we have two additional terminal named drain and source. So this is nothing but drain, this is source, this is what I call as gate, and this is what I call as body or substrate. Yeah, so this is what the difference as MOSFET. So what do we have is we have MOSFET, which are also of now two different types, which is enhancement MOSFET and one is depletion MOSFET. So let me take the basic difference based upon the NMOS structure only, in which we have a P substrate because that is easier to understand since we have done all the derivation based on that. So if we have a N channel enhancement MOSFET, if I say, so if I have this N channel enhancement MOSFET, then what I can say is I have, let's say this is the aux, sorry, not this. So what I have is I have two additional N plus implants over which I have this oxide and nothing but the VG. So this is source, this is drain again, and this is body which is grounded. So in circuit language, what I can write is I can make it something like this. So since the current is going from drain to source, so this is a drain terminal, this is the source, this is the gate, and the body is always grounded, so I'm not making that. So this is how it looks when we make it on from the circuit perspective, and this is the device. So enhancement and depletion, the basic difference is in the enhancement MOSFET, what we have already discussed, that there is a formation of channel basic, which is basically the inversion layer, which is happening after the application of gate voltage. That is after we reach the certain threshold voltage. So if I now say the same about n channel depletion MOS, in n channel depletion MOS, what we have is we already have the channel. So if I make this again, let's say I have this n plus again, but we already have a channel which is having a certain electrons, and on top of that I have this oxide, and this is the gate, this is again the source, this is the drain, and this is the body which is grounded. So in depletion region, in depletion MOSFET, what happens is we have the formation of channel even without application of gate voltage. So what I am trying to say that even if VGs is zero, there is a channel. By channel means I mean inversion layer, or basically a channel of electrons. So I hope this is clear. This is a very basic difference between n channel uh, enhancement and a depletion MOSFET. So yeah, this is it for the basic difference. Now what we'll be doing, we'll be looking for the current characteristics for the same. So we'll be doing the derivation because we have done everything considering the enhancement MOSFET. That is what the practical MOSFETs are. So we'll be seeing how the current versus voltage characteristics look like for an enhancement MOSFET. Yeah. So let's say, let us consider basically, let's say, let us consider we have a n channel enhancement MOS. So what I can make is basically, now we already know that we have n plus source and drain. On top of that, on top of that we have this oxide, and this is nothing but metal gate. This is drain, this is source, this is drain, and this is rounded, which is body. So this is what is nothing but a n channel enhancement MOSFET, where channel, maybe I can denote. So this is a channel. So let's say it is L. So I can say that L is the length of the channel. Then let's say we have W, which is the width of the channel, which will be in the inner side. If I make a diagram like that, so this will be the width, which I'm denoting as W. We don't need to have a certain confusion as of now, because we are not even much interested in width as of now. I'm trying to basically make or to make familiarize with certain terms in the MOSFET. And let's say what we have is, in general, we have the source is grounded, which is grounded, and we in general have the application of the drain voltage, which I'm writing as VD, and this is nothing but VG. So one more thing is, let's say we have, yeah, we have this as Tox. The oxide thickness is Tox. So if we have this, if I make a very basic 2D view in which we have, let's say, source, and here is a drain, which is n plus n plus, we all know. This is oxide, and this is metal, this is gate. This we already know now. So let's say we have a certain channel formation in which we have certain electrons. I'm assuming the channel thickness to be, let's say I'm denoting it with H. So H is nothing but the thickness of channel. So now what we know, at Vg is equals to 0 volts, there is no channel. At Vg is greater than Vt, what happens? Inversion happens. That is after the inversion, what we have a channel, and there is a conductive channel. That is of electrons, and that is between source and drain. So basically, when a channel forms, what do we have? It has a channel potential. So maybe if I try to say that the source is always grounded, that I have done. Let's say I'm applying a certain voltage Vd, and I have, let's say, the gate voltage is nothing but Vg. Yeah. So what I can say that this channel has a certain potential difference between the source and drain. So we know that here the potential is, because it is rounded, so here the potential is 0. Here what we have applied, if I try to write, here we have applied the potential as Vd. So there is a potential difference in between the channel. So I'm denoting that potential difference. Let's say this is x-axis. So I'm denoting it as VCX. So voltage potential across the channel at x distance. So it will be difference for all the x values from, let's say, 0 to L. So this is the channel length, which is L. I hope this is clear. Is there any doubt in this? Uh, is there any doubt in this particular thing? Okay, yeah. Thank you. So let's say we have a channel which has a thickness h, as I have already noted, from drain to source. And what I am interested in, I'm interested in the current from drain to source. So this is what we'll be deriving about drain to source current, which is IDS. And if I write the current density, it will be W times H. So thickness, which will be cross section or at the back side. So it will be W times H. So this is nothing but current density. That is current per unit area. Sorry. So yeah. So we'll be deriving finally about what is this IDS only. Is this, yeah. So we know that we have the current density. If you remember in the previous lectures, a very basic relation is nothing but NQVD, where Q is nothing but the charge, N is nothing but the number of electrons, and VD is nothing but the drift velocity. And can you tell what is this drift velocity in terms of mobility and electric field? Do you remember? If you remember, it is something mu E, that is mu n E, because we have a channel of electrons. So I'm writing as mu n, from which we came to know that this electron density is nothing but nq mu n E. This we already know. Let's say this is equation 1. And electric field is nothing but dV by dx, if you remember correctly. So here what I can write is dVx Vcx by dx, because I have denoted the channel potential like that. And if I put this electric field into this, what I'll get is, I'll get the Js nq mu n E is nothing but dVcx by dx. So let's say this is equation 2. Is there any doubt till here? Till the second equation?
No, exactly.
Okay. And what is this NQ? I hope you remember NQ, as I written in the inversion charge, is a charge per unit volume. Sorry. Yeah. So this is small NQ. And we have just derived that the inversion charge, that is what we are interested in. So in case of a MOSFET, we just derived that what we have, the inversion charge is nothing but Cox times VGS minus VT. That is basically we at least require the gate voltage which is VGS minus VT to have the formation of inversion layer. But that is applied potential was not zero, like there was no channel potential in the case of a MOSFET. But what we have in case of a MOSFET, sorry, in case of a MOSFET, we have a channel potential VCX. So what we can write is now the inversion charge will be nothing but the difference between VGS minus VT, that is same, but we will have a certain potential difference, that is VCX. And since it was the charge per unit volume, so I'm writing now the NQ as, I need to have it as per unit area, so I'll just divide it by the height and everything remains the same. So let's say this is NQ. So this is equation star. Is it clear till here?
Yes, sir.
Yeah. So now what I wrote in the previous was J was NQ mu, what was that? NQ mu n, and then this dVcx by dx. So I've just replaced this NQ by whatever we have got, Cox by H, VGS minus VT minus VCX, and dVcx over dx. So if I write, yeah, so I hope you remember that we have just written J as IDS times IDS divided by W into H, which is the current density. So I can cancel this H, and what I have got is IDS is nothing but W times VGS minus VT minus VCX dVcx. Let's say, yeah, I can write this here. Or what I can write now is IDS into dx is W times VGS minus VT minus VCX and dVcx. So to calculate this current, what we can do is we can integrate both sides. Yeah. So what we want is we want the current across the channel that starts from 0 and that goes till L. And the voltage, it will go from 0 to VD, because at source we have a 0 voltage and at drain we have a VD voltage. So I'm writing S because the source is always grounded. So I can go from 0 to VDS, that is effectively VD only. So now the LHS will be IDS. So X will be from 0 to L. So I'm just writing L because IDS is independent upon the channel. We are assuming that we have all the ID same across whole the channel. And if I integrate this, then what I'll got, this is VGS minus VT. So this is constant. So I hope you know that the constant integration is nothing but X. So it will be VC, in which when I apply the limit, it will be VDS minus 0. And finally, we have VC square by 2, in which if I will be applying the limit, it will be VDS square by 2. So what I can write, this L can go this side, and IDS will be, uh, did I left something? There was this Cox. Yeah, I left this Cox. Yeah, I only left this. So the Cox will still be here. Yeah, still missing out the mobility, which I have again. So J was NQ mu n. So this mu n, I also forgot to write this mu n. So writing, adding this, sorry for that. So what I can write is IDS is nothing but mu n Cox W. This L will come in the denominator by L. And then what I have is, sorry, VGS minus VT times VDS minus VDS square by 2. Uh, does it make sense? Is there any confusion how we have got this in the integration or anything?
No, sir.
Okay. So
Clear.
now, sorry, is there any doubt?
No, sir.
Okay, okay. So now one more thing that we should be taking care of, that this is only applicable till the VDS is less than VGS minus VT. And this is what we call as a linear region, in which the MOSFET acts as a resistor basically. By resistor, I mean that it is linearly changing with VD, because VDS will have a very small VDS, we know. So VDS square is negligible. So if I just for now don't see this as a term, then it is linearly dependent upon VD. So that is what it is making as a resistor, that IV is linear. This happens for a resistor. So now we did two things that I guess we did not think much about before doing. Give me a moment. So the first thing was, sorry, yeah. So the first thing that we did was, in the while doing the derivation, we wrote VD as mu e. Do you remember this VD versus mu e curve? Sorry, VD versus e curve. It what happens is it is a linear curve, but then the velocity saturates due to the velocity dash, the saturation, and it happens after a certain critical electric field. So we have only assumed that VD equals to mu e. So this particular thing holds only for smaller, or only for only till critical electric field. That is smaller electric fields basically. So for smaller electric fields, we know that the VDS will be low. That is what we have written. So VDS will be low. That means VDS square can be neglected, and we will have a exact linear relation between IDS and VDS, or IDS is inversely proportional, sorry, directly proportional to VDS. And the second assumption that we took, that we have not cared of, we have assumed that the channel thickness, basically H, is constant. But ideally, it will not happen that the channel thickness will remain constant, because if we start to increase this VDS, what happens? The thickness of the channel will not remain constant. I'll let you know how it will change. So if I make very quickly, let's say this is source, this is drain, and if I, this is oxide, and over this we have the gate. If I keep on increasing this VD, what happens? We have a channel like this. The electrons will be like this, and we have a channel like this, which is known as the tapering of the pinch off point. So I'll let you know what is happening. So let's say what I am doing is I'm considering 2 points in this particular diagram. One is this point, I'm naming this as 1, and one is this point, I'm naming this as 2. So first of all, why channel thickness is not constant? This is the major question. So if I talk about the first region, that is this region 1 that I have made. So if I made a very crude diagram, so let's say this is gate, this is the inversion layer, and this is the semiconductor that we have. So there is a inversion, right? We know that there is a channel here. Why? Because this VGS minus VC. So here VCX is nothing but 0, right? And here we see x is nothing but Vd. So this, if this is 0, so it is, we know that for inversion layer, what is the criteria? VGS should be greater than VT, right? So if this is, the channel potential is negligible or 0 here, we have the inversion layer. That is for surety. So we do have this channel in the, in region 1. But if I do the same for the second case, so what is happening? Let's say again we have the gate, we have the inversion layer, we have the semiconductor. So what I can say here is VGS minus VC is nothing but, or if I say maybe VGS minus VT is nothing but it is less than the channel potential VCX. Why? Because we have a very high drain voltage here. If I am keep on increasing this, we are going away from making the inversion layer. Do you understand this point? That if we are effectively increasing the drain voltage, we are reducing this VGS minus VT. So that is what, that is we are due to this the inversion layer will not form if we make the VD as high as, which is greater than that of VGS minus VT. Do you able to understand this? Uh, Maybe I can write that what I'm trying to say is, for one, what I'm saying is gate voltage is strong enough for the first point to overcome the channel potential VC. That is VGS minus VT is still maintained to overcome the channel potential VC. But for second, what is happening? We have a case when the channel potential is large enough, that that is VDS is large enough such that VGS minus VT is, like VDS is greater than that of VGS minus VT, which is what it is doing. It is not helping in forming the channel out. Does it make sense? That is, we cannot have the inversion layer if, let us, if we start heading more towards from drain to source, if we increase more and more voltage, what will happen? This will go further beyond. So it is till now, it is here, it will go like this, it will go like this, and these points are nothing but known as the pinch off points. Are you able to understand that how by increasing the VDS, why are we going away from these points and why it is opposing the formation of the inversion layer? Does it make sense? Okay, yeah, that is good. So if it makes sense, then what do we have? We have the tapered off channel, and the moment this VGS minus VT is getting greater than that of VDS, the channel is getting tapered off and there are no electrons in the channel, as you can see. Or if I say maybe this diagram, if you see, so there are no electrons here if the channel is like this. So that is what is known as a pinch off point, and for this VDS is greater than that of VGS minus VT. So now if we think more, that if we are if we assume that the transistor is working in linear mode of operation, give me a moment. I'm sorry for the glitch, but am I audible?
Yes, sir.
Okay, yeah. So yeah, so what I was saying is that for a higher VD, this potential is large enough to have this oppose in formation of the inversion layer, and there are no electrons available in this region particularly, and this is what we call as a pinch off point. But now what we have further is at this particular voltage, basically the channel is getting pinched off. So if you can see this, the channel is getting pinched off. This is what is a pinch off point. That is, I've already discussed. I hope we were there till here when the internet went down. So after this, even if you increase more and more VG, what will happen? There will be no further formation of inversion layer, and that is what we call that if this VDS is greater than equals to VGS minus VT, we call this region as saturation because the current saturates basically. By saturates, what I mean is, so we have done two experiments now. Say this is VDS, this is IDS. So we had a certain voltage which is VGS minus VT. Before that, the current was almost linear, and after that, it is saturating. So this is a very ideal plot of how ID VD looks like. And if I say that if VDS is greater than, sorry, VGS minus VT, as I said, the current saturates and becomes independent of VDS, because if we even increase more VDS, there is no channel. And once it happens in saturation operation, uh, it behaves like a current source. Basically, the MOSFET behaves like a gate controlled current source, which is independent of VDS. So what I can write this, since it becomes independent of VDS, so which is nothing but VGS minus VT. So in the previous relation that we got, which is this VGS minus VT into VDS minus VDS square by 2. So what I can do is I can replace this VDS here and here also, and what I'll get is IDS is nothing but UN Cox W by L. This is VGS minus VT, and this VDS is also VGS minus VT minus VGS minus VT whole square by 2, and this IDS is nothing but mu n Cox W by L. So this term will become whole square. Let's say this is a square and this is a square by 2. So if I minus them, it will be a square by 2. That is VGS minus VT whole square by 2. So this is the case when this VDS is even increased beyond VGS minus VT. So this is the derivation for the saturation region now. The previous one was a linear region. So in linear region, the MOSFET was acting like a resistor, and in saturation region, it is acting like a current source, which is calculated or controlled by the gate voltage. So if I write like together the whole summary of that, so what we have is we have IDS, which is mu n Cox W by L VGS minus VT to VDS minus VDS whole square by 2 when we have when we have VDS less than VGS minus VT, and we have mu n Cox W by L VGS minus VT whole square by 2 when we have this greater than that of VGS minus VT. And this region we are calling as saturation. This region we are calling as linear. And one more thing, if Vg is not even greater than or less than Vt, so there is no conduction, right? So 0 is IDS ideally, and this is what we call as cutoff region. So if I make the exact plots, it looks like this something. This is IDS, this is VDS. It looks like this, in which we have this is saturation, this is linear. and this particular thing is VD sat or VGS minus VT. Is there any doubt till here?
No, sir.
So if you're able to get that, then I guess we'll be able to do some of the numerical problems. Further, there is one more concept that I left in the previous class, which was effective oxide thickness. So let me cover that also, and then we'll be going towards the numerical. So we have, let's say we have a MOS cap in which we have this oxide layer, which is having TOX. Then we have this gate. So do you remember how can we calculate the oxide capacitance for this particular thing? Let's say epsilon ox is the permittivity.
Epsilon of A by T
Yeah.
of.
So if I say let this is per unit area, so what I can write, this is epsilon ox by T ox. So this is per unit area. So it has a unit of microfarad per centimeter square, let's say. So what do we have in general? We have in general the MOSFET oxide as SiO2. So now as we have now seen some of the formulas, in all the formulas, if you see something something, so there was two different formulas, but this remains the same. And in this we have this mu and Cox, which is epsilon ox by Tox W by L. The whole motive of this particular semiconductor is to increase I. We have more and more current somehow. What we can do to have more and more current? Either we can increase this W, or either we can decrease this length, or either we can increase the capacitance, or either we can increase the mobility. This is how we can increase our current. But if we increase the width, it will consume more area, which implies more power consumption, right? So this is not good for us. If we increase capacitance, what will happen? It will have a delay in the circuit because the time constant is nothing but RC. So if I have more if I have more C, it will be having a more time constant. And if we cannot have impact on mobility because it is material dependent, so it is also fixed. And if we increase a very shorter length, this is what we do, which is what we call as technology scaling. But if we go to in nanometers, there are a lot of leakage currents. Like I'm telling it very in a crude way now, but the main objective is how can we increase this IDS. So we know that this Cox is nothing but epsilon ox by Tox. But if we decrease this Tox, there will be can be leakage because we are applying more and more gate voltage, and we have this minus minus here. So if we have a very thin layer of this SiO2, what can happen? There can be the passage of these particular electrons from the gate to the basically the channel, and there can be more leakage. So we are not interested in even decreasing the oxide thickness. So what we can do, the one thing that we have got is we can increase the epsilon or the permittivity basically, and it is fixed for SiO2. So what in general we do, we take the materials which have high value of permittivity. One such example is HFO2, which is having a permittivity of relative permittivity of 25. And SiO2, as you already know, has a relative permittivity of 3.9. I hope you do remember that. So if we have, let's say 3.9 instead of 25, so this current will increase, right? Because of the higher permittivity of HFO2. So this rises to a concept of EO2. So what we do is, instead of applying oxide layer as SiO2, we apply a layer of HFO2 and we calculate the effective oxide thickness such that capacitance remains the same. So what was that? Cox was epsilon ox over Tox, right? So if I apply, let's say HFO2, so it will be epsilon of HFO2 over the thickness of HFO2. So this should remain same even if we are applying the different materials. So what I can write is Cox should be equals to CHFO2, and Cox is epsilon ox by Tox, and the effective thickness is always calculated with respect to SiO2. So I'm writing this Tox as EOT now, and this is nothing but epsilon HFO2 by THFO2, which will give me a EOT of epsilon ox by epsilon HFO2 multiplied by thickness of HFO2. And we know that this is 3.9 and this is 25, and this is thickness of HFO2. So what we do need to have in the structure, we need to have a higher thickness because, sorry, if I take THFO2 around 5.64 nanometer, then this particular EOT will come around to be 1 nanometer. So are you able to understand that while fabrication we need to put 5.64 nanometer of thickness of the oxide if we are using HFO2 as a material to get the equivalent SiO2 of 1 nanometer. Basically what I'm trying to say is, it's a this is SiO2 which is 1 nanometer. It is equivalent to, if I'm making a structure, it is not scaled but it is equivalent to 5.64 nanometer if I'm using HFO2. Does it make sense? Any doubts in this? I can explain again if there is any doubt. Please let me know.
So can you explain once again, please?
Okay, sure, sure. So what I am trying to say, okay, let me explain in a very simple way. So let's say I have a MOSFET, MOSCAP basically, not MOSFET, and I'm using SiO2. I'm calculating the oxide capacitance, which is nothing but epsilon ox by Tox, and I'm calling this Tox as effective oxide thickness. And this epsilon ox has a certain value 3.9. So to increase the permittivity, what people do, they use material such as HFO2. So HFO2, if I now try to calculate the oxide capacitance, it will be epsilon of HFO2 over thickness of HFO2. So these two structures should ideally act as the same, right? So what I can write is this Cox should be equals to the capacitance over HFO2, and what I can write is basically EOT will be something, if I solve this again, so it will come out to be epsilon ox over epsilon HFO2 into T of HFO2, and what we have is epsilon ox is 3.9, epsilon of HFO2 is 25. So this is what I wrote there, and what I'm now saying that if I take the thickness of HFO2 as 5.64 nanometer. So now if you put this in this formula, the EOT will come out to be 1 nanometer. So what is basically it is denoting is, if I have took 1 nanometer of SiO2 initially, and if I replace it with HFO2, I need to have a thickness of 5.64 nanometer for that. Then only then these two things will have the same characteristics. Make sense? That,
Yes, sir.
yeah, so that 1 nanometer of SiO2 is basically equals to 5.6 nanometer of HFO2. During the fabrication, we need to have a thicker layer of HFO2. Is it clear?
Yes, sir.
Okay, so if it is clear, then you can try this numerical. This is a very simple numerical now. So we have a MOS capacitor in which we are using this high K dielectric material, which is basically 25. So it is HFO2 with as a replacement for a SiO2 layer. which has a permittivity of 3.9, and it is given that the thickness of SiO2 is 10 nanometer. So basically you know EOT is 10 nanometer. You need to calculate the equivalent oxide thickness if, so what it is saying is we have a SiO2 which is 10 nanometer. You need to calculate the same effective oxide thickness if I use a material which has a permittivity of 25. This is what we just did basically. So for 10 nanometer, what we require to have a EOT of, so you need to calculate the EOT for the high K dielectric. So do you understand the question? What you need to do? Please let me know if you understand.
Can you repeat once again?
Sorry.
Can you repeat, sir?
Okay. So it is saying that if I need to have a EOT of 10 nanometer, and if I have a material HFO2, so what thickness of HFO2 should be there to have the equivalent EOT of 10 nanometer? Like I just said you that 5.64 nanometer of HFO2 physical thickness is giving me equivalent 1 nanometer EOT. So now what it is asking that for 10 nanometer EOT, what should be the physical thickness of HFO2? Make sense?
Yes, sir.
Yeah.
Ag-
So do you want to try it? Maybe it is already solved now. So this is an accurate calculation. So it will come around 56.4 nanometer. And if we have a very crude calculation, then 6.5 nanometer of HFO2 is equivalent to 1 nanometer EOT. So the closest answer to this is option C, which is 65 nanometer. Does it make sense that we require physical thickness of 65 nanometer to achieve a EOT of 10 nanometer? That is 65 nanometer HFO2 is equivalent to 10 nanometer of SiO2. Make sense? Please let me know if there is any doubt in this. Okay, fine. So now we have already covered the most important three concepts. One was the inversion charge. The second was EOT, which was left in the previous class. And the third is the derivation of IV characteristics of MOSFET. So now we'll be having the question similar to solving the MOSFET. So we have covered what is the difference between enhancement and depletion. So this is the first question that we have, that for an ideal p-type depletion MOSFET, choose the correct statement. Do you want to give it a try? Uh, Maybe I can give you 2 minutes and think which option suits the best, and let me know. What do you think is the answers? So let's say options are A, B, C, D, E, F. So you can take 2 minutes and then let me know. Is it fine?
yes, sir.
Yeah. Any guesses? So if you remember that, what do we have that for depletion type of MOSFET? What do we have? Do we have the inversion layer even without the application of bias voltage, or we need to have the formation of that?
No, sir. Already inbuilt channel will be there in the depletion
Yeah.
MOSFET.
So if there is already built channel, so let's say let's see one by one each of the options. So it is saying that the inversion layer is created for an applied bias greater than threshold. So this is the case for enhancement, right? But it is asking for depletion. So let's go to the second option. The electron inversion is created. So again, this is enhancement. And this is a P-type depletion MOSFET. So what we will have? We will have an N-type substrate, and in which the layer that will be formed is for the hole. So this is correct for enhancement. This is even a wrong statement that electron inversion layer is created. So both of them are incorrect because they are talking about enhancement first of all. The third option is a hole inversion layer exists for zero applied bias. So we have option that the electron inversion layer is exists for zero bias. So either this is correct or this is correct. So this is again incorrect, incorrect. So what can be the answer? This one or this one? What type of inversion layer will be created if we have a P-type MOSFET? If it is getting confusing,
Electron inversion.
so let's say we have a NMOS. NMOS may we have P-type substrate. The inversion layer is created because of,
Applied voltage.
yeah, applied voltage is fine, but is it electron or is it holes?
Electron.
And in this question, what we have PMOS.
So it means hole.
Okay, so inversion layer will be of,
Hole.
yeah. So the correct answer to this will be option C. Make sense?
Yes, sir.
Okay, that's good. So if it makes sense, then we can move forward to the further second problem. So now what we have a N-channel MOSFET, and we have all the parameters given. So we have given K. So K is basically nothing but mu and Cox W by L, and we have one as Kx, which is mu and Cox. We have been given K, we have been given W by L, we have been given Vt, and it is saying the drain current ID at VGS equals to 0.9 and VDS equals to 1 volt. So first of all, can you tell whether the transistor is in linear region or saturation region? How can we do that? What is the criteria?
In saturation, it will be VDS should be greater than or equal to VGS minus VT. If it is
Yeah.
less than, it is.
Okay, yeah. So VGS minus VT, and this is the criteria, and we have everything. So VGS minus VT is given in the question. VGS is zero point 0.9 and VT is zero point 0.4, and it is giving out zero point 0.5, and VDS is given as 1 volt. So transistor is in,
It is in saturation region.
yeah, it is in saturation. And for saturation, what is the formula? We have K times VGS minus VT whole square by 2. And we have each and everything given. So K is already given, so we don't require W by L. So it is 1 milliamps, 1 milli by 2, and VGS minus VT is zero point 0.5. So zero point 0.5 whole square. It is 0.25, 0.25 by 2 is 0.125 milliamperes. So is there any option? Yeah. So 0.125, sorry, not microamperes, milliamperes. So option A, B, E is the correct answer. Is it clear? This was very straightforward, I guess. Any doubts?
No, sir.
Okay, so if there is no doubts, then try this. This is a similar question in which the VG and VD are different and we have certain different values. And let me know what is the answer that you are getting. So do you want to try it? Please let me know. Otherwise, we'll.
Okay, sir. I'll do it.
Okay, fine.
B is the answer, sir. 0.0502.
Okay, so what I think option B. Okay, so let's try it out. So we have N MOSFET, mu n Cox is given, W by L is given, Vt is given. Okay, so first of all, VGS minus Vt is zero point 0.8 minus zero point 0.4, which is zero point 0.4, and VDS is zero point 0.1. So it is in linear. So if it is in linear, we can calculate quickly. Un Cox is 0.18 milli, and then we have W by L, which is 8. VGS minus VT is zero point 0.4 times zero point 0.1 minus 0.01 by 2. So maybe can try to calculate this. Yeah, so it is coming out to be zero point 0.8 into gram. So it is coming out to be 0.0504 milliamps. Yeah, option B is the correct answer. That is good. So this was a very straightforward question. Is there any doubt in this?
No, sir.
Okay, so let's move ahead. I'll take the SS question later. First, let's do the numericals. So we have the ID versus VGS characteristic determined experimentally for a N-channel MOSFET, which is given below. So we have been given 2 points. One is VGS is given as 1.5, and the corresponding ID is 25 microamps. And at VGS equals to 2.5, the corresponding IDS is 65 microamps. VDS is given as zero point 0.1 volts. Oxide capacitance is 8 times 10 to the minus 8 farad per centimeter square. So the first question is the mobility of carriers in the inversion region is. So can someone tell how can we calculate this? Any guesses? So first of all, we are talking about inversion, and even in inversion, we have a such low VDS. So what it is showing is even if the VT is at highest 0.5, VDS will always be less than VGS minus VT. That makes the transistor in linear region, right? And for linear region, we have two different equations given that what is IDS for particular VGS. So can we have two different equations and calculate the mobility? Uh, are you able to understand what I'm trying to say?
Just can you repeat once again?
Sorry?
I didn't get you, sir.
Acha, you didn't get it. Okay, okay, fine. So first of all, the transistor is in linear region. So we know that IDS is mu n Cox W by L VGS minus VT into VDS minus VDS whole square by 2. So what I'm saying is we know that what is IDS, what is Cox W by L, what is VGS, VDS and VDS. We know everything. So we have two different cases. Let's say this is, I'm just assuming this is 1, let's say. So it will be mu n. Let's say this is something called as B. Let's say this is A, this is B. And again, this is some constant C minus Vt is not given, I understand, minus T square by 2. Right? So we have one more case in which we have we have given VGS and VD and corresponding ID is given. So we can have two equations in which we will have two variables, one is mu n and one will be VT. And from two equations of two variables, can we calculate both mu n and VT?
Yes, sir.
Yeah, so try to do that. Maybe I can give you 5 minutes for this because it might take more time. So let me try to write the equations for you. So the first equation is at 25 microamps, we have mu n Cox is what? 8 into 10 to the minus 8. W by L is 10. It is given that W is 10 micro. You can see here. The width and length are 10 micro and 1 micro. So W by L will be 10. And VGS for this case is 1.5 minus VT times VDS is fixed, which is zero point 0.1 minus zero point 0.1 square by 2, which is 0.005, I guess. And the second equation will be 65 microamps is mu n times, this will remain same. This will be no 2.5 minus Vt into zero point 0.1 minus 0.005. So do you want to try and calculate it or I should do it?
No, sir, I'll do.
Fine. Just try it and let me know what is the answer. You need to find mu n.
So one thing doubt, sir.
Yeah, yeah. What is the doubt?
Uh, we have to calculate epsilon, not just means
Epsilon naught?
mobility
Yeah, yeah.
of the. So epsilon, how to calculate epsilon, sir?
Uh,
Here to here it is mu
hmm.
mu n.
Hmm.
So epsilon here it is
Ep-
not, it does not appear here.
epsilon is why is epsilon coming into the picture? Cox is epsilon ox by Tox, right? This is what you are saying, epsilon. Uh, Please clarify if you are
The
saying
mobility.
mobility. Okay, so we have two equations in which we have two variables. So let's say in a very simple way, 2x plus 3y is something 5 and 5x plus 6y is something 7. So you can calculate x and y, right?
Yes, sir.
So this is what this is. So mu n is one variable and vt is the another variable. So maybe I can also calculate side by side, that will give more clarity to you. So if I talk about, let's say, this equation first, so what I can write is, where is that? Yeah. So 2 minus something something is there. So if I, let's say this is 10 raised to minus 7 and so I can write the first equation I'm writing, 25 micro is minus 6. Sorry. So minus 6 will give minus 2 and this is minus 1. So this will be 0.8. 0.8 means 250 by 8. Basically 250 by 8 mu n is nothing but 1.5 minus Vt, zero point 0.1 minus 0.005. And if I plus it, this is very less. So I can neglect this term maybe. And if I do the 10 division, so finally it will be 250 by 4 mu n is equals to 0.29 minus 0.15 minus 0.005 and this is 0.2 Vt. So this is the first equation that I got. Does it make sense? Like I have done the basic calculations. I have like open the bracket, it is 0.25 So 0.25, sorry, this is 0.15 and minus something, it is giving out something 0.29 minus 0.2 VT. And similarly for second thing, I can write 650 by again 4 mu n, it is 0.49 minus 0.2 VT. So now what I can do, I can subtract these two equations. Let's say this is, I'm subtracting, this will be plus, so this will get cancelled out. And what I have is 0.49 minus 0.29 is 0.2 is equals to 650 minus 250 is how much? 400. 400 by 4 mu n. So this will give me mu n is equals to 100 by 0.2, which is 500 centimeter square per volt second. Does it make sense? Like I've done the basic calculations. 500, is there any option? Yeah, there is some option. Is there any doubt in this? I've done the basic maths here. Please let me know if there is any doubt.
Clear, sir.
Okay. So if we have calculated the mobility, the second part is we need to calculate the threshold voltage. And it is saying ignore the VD square term. So can you do that? This is very easy now, I guess. We have everything. Do you want to try or I'll do it?
We will do, sir.
Okay, so maybe take 2 minutes just because this is very easy now. Because we have everything. We have mu n, we have Cox, we have W by L, we have VGS minus VT, and we have VDS. So this is what you need to calculate. Or we have IDS also, you need to calculate the VT. Maybe take 2 minutes and then let me know what is the answer.
I think option number 5, sir.
1, 2, 3, 0.625 you are getting? Okay, so let me try to calculate. So let's say I'm taking any one case. So I'm taking 25 micro. So I'm ignoring this. 25 micro. 25 into 10 is minus 6 is 500. Cox is 8 into 10 given minus 8. This is 10. VGS is 1 minus Gaga VT 2.1. VGS is 0.1, right? Uh, so 10 is for minus 2 minus 1. This also gone. This is 2. This is, I guess, 16 now. 16, 10 by 16 is 1.5 minus VT. VT is 1.5 minus 10 by 16. So something like that. What is this? 10 divided by 16 minus 1.5. I'm getting 0.875, which is option B. I don't know. Is there any calculation mistake that you have done? I hope you understand this is basic calculation only. Any other answer that anyone else has got?
No, sir. Correct. 0.8.
Okay, so I hope this is correct. So let's move forward. I guess this is clear. If this is clear. Okay, so maybe this is theoretical. Let's take numerical first because this is a good question. This is a great question. So it is saying that the slope of the IDVG curve of an NCL MOSFET is given as, so basically slope is d by dVg is given as 0.02 at VDS equals to 0.1 volt. For the same device, neglecting the channel length modulation, so this we will cover in the next lecture, which is one of the short channel effect. The slope of the under root ID versus VGS under saturation is approximately what? So first of all, the first is the linear region. So linear region, we know that IDS is nothing but what is this? I'm writing K for now. K into VGS minus VT times VDS. So if I do the differentiation with respect to, maybe I can write the second term also. If I do the differentiation with respect to VGS, which is given in the question, it will be nothing but K times VDS, right? Is there any doubt in this?
No, sir.
So this is given as 0.02 at VDS equals to 0.1. So what I can write is K into 0.1 is 0.02, which will give me a K of 0.2. I hope it is clear till here. If there it is not, please let me know right now only. And it is asking that in saturation, what is the slope of under root ID by under root. So basically what it is asking this del under root IDS by del VG. What is this at saturation? So at saturation, the equation we know is it is nothing but K by 2 VGS minus VT whole square. So can I write under root IDS is under root K by 2 VGS minus VT? Can I write this?
Yes, sir.
So now if I'm doing the differentiation with respect to under root by VGS, it will be nothing but under root K by 2, right? Any doubts?
No, sir.
And K we have calculated, it is point, what was that? It was 0.2 or 0.1? 0.2.
0.2 only, sir.
Okay, I've written everything correctly. Yeah. So it is what, 0.2 divided by 2. So it is under root 0.1, which is uh, which is what? Which is what? Please let me know what is under root of 0.1. Okay, so it is 0.316.
0.316.
Yeah. So the answer to this question is, so this is a gate question which has no option. So the answer is 0.316. Is it clear to everyone?
Yes, sir.
Okay, good. So let's move ahead. So this we have already discussed in the first part during the derivation that we have different regions. So this B is a linear region, C is a saturation region, and if Vg is not even greater than Vt, then it is the cutoff region. So A is cutoff, B is linear, C is saturation. Cutoff is also known as sub-threshold because it is below the threshold voltage. So sub-threshold linear. So option C is correct. Is it fine? I'm not spending much time in this. We have done the derivation in the first part. If you have missed it, you can watch the lecture on the YouTube also. That is fine. So let's move ahead. This is a very good question. So it is the gate question which has come this year only. So this is a 2024 question. I guess this has been given in the assignments also. to you. So it has a NMOS transistor which is operating in linear region. It is given that ID is this and VD is this. Keeping the VG constant, the VDS is increased to 1.5. W by L is given. We need to find the transconductance. So maybe I can elaborate on that. So transconductance is nothing but the differentiation with respect to Vg, which is what we have done in the previous question. So you need to calculate this. So let's give it a try. Yeah. So first of all, it is saying that in linear region. First part, it is in linear. It is saying that ID is 5 micro.
Sir, your mic is muted.
Okay, my bad. So I hope it is till when can. So did you hear this particular thing? Is it clear?
Yes, sir.
Okay.
Just
So
now.
okay, fine. So for this, now the question says that in the linear region, it is given ID is 5 microamps and VDS is 0.1 volts. And what I said is the transconductance is nothing but the differentiation of the ID with respect to the gate voltage. So in linear region, we have one condition given. So let's try to solve this first of all. So in linear, we have done this mu n C ox W by L, and it is nothing but VGS minus VT, VDS minus VDS square by 2. So let's just calculate it. It is 5 micro is mu n C ox W by L is given. Yeah, mu n C ox. So this is mu n C ox W by L. Sorry for the glitch. So this is 50 micro, and what we have else is VGS minus VT. VGS is also given, I guess. No, VGS is not given. VDS is given is 0.1. So this is 0.005. So maybe this is nothing but 10. So 1 by 10 is 0.1, 0.1, 1, and VT is given kya? VT is not given. Okay. So 1 plus 0.5 into 0.1 is nothing but VGS minus VT. So VGS minus VT I'm getting as 1.05. Is there any doubt in this? I've just done the basic calculation. So this is 0.1. I have divided everything by 0.1. Is it clear?
Yes, sir.
So if now the question says that keeping the VGS constant, the VDS is increased to 1.5. So VDS is 1.5 and VGS minus VT is 1.05. So the transistor is in saturation, right? So in saturation, what we have is IDS is nothing but, maybe I can write mu and C of W by L, VGS minus VT whole square. And what we need to calculate, we need to calculate the transconductance. So it is nothing but ID by VGS, which will be nothing but, sorry, this is by 2, which will be nothing but mu n C ox W by L. Okay, sorry, I think it vanished. So what I have calculated is VGS minus VT was 1.05 volts, VDS is 1.5 volts. So what I am saying is GM is nothing but del IDS by del VGS, which is, first of all, IDS in saturation is K by 2 VGS minus VT whole square. So what I can write, the differentiation of this will be K by 2 into 2 times of VGS minus VT. So basically GM will be mu n C ox W by L times VGS minus VT. Is there any doubt in this? Please let me know if there is any doubt. So if not, this is
No,
okay.
sir.
So this 50 micro, and what we have is the current is need to calculate it in micro. So I'm not writing micro. So it is 50 into 1.05 microamp per volt. So this will come out to be, I guess, 10.5 into 5. So this is 25, 52.5 microamp per volt, which is option. Is there any option? Yeah, option C. Is it clear, everyone? Please let me know if this is clear.
Yes, sir, but saturation, when saturation, sir, occurs,
Okay, why saturation is because the question says that VDS is, sorry, 1.5, and we have calculated the VGS minus VT is 1.05. So VDS is greater than VGS minus VT, which is saturation.
okay, sir, yes, sir.
Yeah. So I hope all the doubts are clear, and we have already covered all the MOSFETs and the derivation also in the initial part. So in the initial part, we covered the inversion charge and the derivation of the MOSFET, that how it comes out to be this equation. You can take a look in the YouTube video also if you have missed it somehow. So basically, we have almost finished with the MOSFET part, and now the further weeks will include more of the interview type of questions. That is the short channel effect. That is what they ask if you want to pursue a career in VLSI. So we'll be having a very good overview of what are the short channel effects, and we'll do some of the questions related to that in the next week. So I hope this is fine for this week. If you have any doubt, you can ask. Otherwise, we can dismiss the session for now. Any doubts, anyone? If not, we
No,
can.
sir. Clear.
Okay, then thank you everyone for joining. Let's meet next week at the same time.